Hello everyone, this is Mrs. Hanson again, carrying on our lessons in Chapter 12. We have two more sections we'd like to talk about. Section 9, reactions of alcohols, either being substitution or elimination. And again, an opportunity to bring back some previous lessons. We've been working hard all semester on getting a strong foundation on SN1, SN2 reactions. And then in Section 12, we're going to look at yet some more reagents that will oxidize alcohols, kind of the opposite of the earlier video on reduction. So let's go ahead and begin looking at how to turn an alcohol into an alkyl halide. So this is beginning with an alcohol and turning it into an alkyl halide, either a chlorine or a bromine being at the target. So substitution and elimination, where we take one functional group and convert it into another. This time we're starting with the alcohol functional group, and we like to end with a halogen in its place. So what are some reagents and mechanisms that allow us to do this transformation? And the first one I'm going to bring us back to is a section 7.12, known as SN1 reactions, where we can use a tertiary tertiary alcohol and convert it into a tertiary alkyl halide. So starting with the alcohol and ending with the halide. Notice that on the arrow is a simple HX that can represent HBr or HCl, that either of those halogens will work via this mechanism. Now remember, we said that the alcohol is a bad leaving group, and so we still need that primer step to turn that alcohol, hydroxyl OH, into a better leaving group, and that's the source of the proton on the HBr. So again, this hydroxyl group is a poor leaving group. It doesn't pick up its electrons and just leave. It doesn't do that because it cannot stabilize the negative charge very well. So by protonating, a proton transfer, by protonating the alcohol, and that's what we're going to label this as a protonated alcohol. I could spell it right. Protonated alcohol. That turns this into a better leaving group. And with an SN1, a unimolecular reaction mechanism, the rate determining step is the leaving group must leave. And so that's what we see in this particular portion of our mechanism. We've converted the alcohol into a protonated alcohol, and then the leaving group leaves. And that's what this minus H2O. And remember, we have an sp2 carbocation intermediate with the SN1 mechanism, meaning that you can have rearrangements occur. And that's why we're looking at specifically using a tertiary alcohol with this mechanism to avoid rearrangements. We have the most stabilized carbocation form in that tertiary position. This bromide that was generated from the proton transfer then serves as the nucleophile and attaches on to create that nucleophilic substitution. So the nucleophilic attack creates a tertiary alkyl halide, and the mechanism is complete. So if we're given a tertiary alcohol, simply add across an HX, or let that represent HBr or HCl. You'll remove a water, and that's simply because we had to protonate the alcohol and then let the water act as the leaving group before the bromine can add on. What about an SN2 reaction review, going back with a primary alcohol? With a primary alcohol, the carbon that's attached to the hydroxyl group is attached to just one other carbon, so we'll see that at the terminal end of the chain. Again, sitting on the arrow is HBr, turning the leaving group that's poor, the hydroxyl group, into a leaving group that is better, a protonated alcohol group, HOH. And then notice that we have the same result, but we just had a different mechanism to get there. We had a bimolecular collision, that the bromide is going to go after this electrophilic carbon, forcing the leaving group to leave all in one step. And so remember, we had 100% inversion if that is indeed a chiral center. So just thinking about that stoichiometry, but that stereochemistry, this is not a chiral center, but if it had been, we were looking at just 100% inversion to remind ourselves of the SN2 mechanism. It works well for bromine, HBr, across the arrow. But remember, if we're trying to add chlorine as the halogen, adding HCl to a primary alcohol is so sluggish it doesn't work well unless we have the presence of the catalyst. And the catalyst that is used is zinc chloride, which is a metallic salt, right? Zinc chloride, ZnCl2, built of 2 ions, a zinc and 2 chlorides. So when we crisscross, we come up with ZnCl2. I emphasize that because the catalyst is a salt, it's water soluble. It must be in an aqueous solution to make this occur, just as the acid is, HCl. And so we have a limit to how efficient this is just based on the alcohol's solubility. So in the first section, we talked a bit about the physical properties of alcohols. And if we have a short chain, such as less than 6 carbons, we would say that the hydrophobic end, and we labeled this the hydrophilic end, water loving, water hating. And if this tail is short enough that we can get it to be water soluble. So this technique is only good to deliver a chlorine on an alcohol of 6 carbons, less than 6 carbons. About 6 carbons, you're getting to the where it's slightly soluble but difficult to get into solution. And so you can see that the zinc actually plays a role in creating a better leaving group. Instead of protonating the alcohol, you put the zinc chloride onto the oxygen, and then we have the chlorine force the leaving group to leave. But only select this process if you're trying to add a chlorine to a very short primary alcohol. It's very limited to its effect as the alcohols get larger and larger because they are not water soluble and therefore will not interact with zinc chloride. Now we understand we've learned a second way to convert an alcohol and get it to leave is through a tosylate compound. And so sitting on the arrow, we can see tosylate chloride and a workup of pyridine. Now pyridine, of course, you know, has the nitrogen base in it. So pyridine, think nitrogen. The workup is the same idea. Here we're starting with a secondary alcohol containing a very bad leaving group. We add the tosylate compound to make the oxygen a better leaving group, and then the leaving group leaves. And remember, this would just be a mechanism there where the X negative, is it bromide or chloride, will add on, then force that collision to make the leaving group leave. And we see a 100% inversion of configuration with the SN2 mechanism. So just a reminder, that mechanism, because it's a bimolecular, you're going to have both dashes. Here we started with a wedge, so 100% is going to come out as a dash, 100% inversion. So tosylene chloride and a workup of pyridine just simply changes the leaving group into a better leaving group. And then here, notice we had NaBr. So if the halogen being added in the second step is a bromide, you would see an inversion of the halogen bromide. If you had a source of chloride, you could add a Cl across the bond there as well. We can also use primary and secondary alcohols to create halogen compounds by using SOCl2 called thionyl chloride, or phosphorus tribromide, and notice that's PBr3, phosphorus tribromide. And this is also via SN2 process and really have the same outcome as a tosylate chloride compound, turning the OH into a better leaving group. So the same process. Let's kind of just share that mechanism. Overall, if I have a bad leaving group, an alcohol group, and I see on the arrow SOCl2 in a workup of pyridine, Notice that this is a source of chlorine, very specific to the addition of chlorine. You'll exchange the hydroxyl group into the chloral group. Let's see how that works. So thinking about the mechanism, how do I get from the left to the right side? And that's this journey. You can see the role of the reagent SOCl2 with the hydroxyl group reaching out to the sulfur, which is slightly positive just based on electron distribution. By adding on, you've created a better leaving group. So think about this as a poor leaving group and eventually converting it to a good leaving group, which gets up and leaves. Through the process of adding on the SOCl2, we notice that the oxygen develops a +1 formal charge. And so to quickly eliminate that unstable configuration, you'll see that the pyridine, this is the solvent right here, is going to deprotonate that oxygen, reaches out. And that's the only role of the pyridine at this point, is to just deprotonate that reagent, forcing this bond to collapse and create two sets of, two electrons there to alleviate the formal charge. So now all of a sudden, as we move from this, the formal charge is alleviated by plucking off that proton from the solvent. And now we have a better leaving group and a bimolecular collision. Remember this chloride that was expelled over here becomes the nucleophile over here. And the nucleophile is going to attack, forcing the leaving group to leave, and we've added on the chlorine. Now for us at this stage, I wanted to show the how. We're just really going to be asked to go from the left to the right. And I'll do the same. I'll discuss with you the PBr3, phosphorus tribromide. Notice that this is very specific to adding a bromine. So again, if you want to add a chlorine, SOCl2 in a workup of pyridine. If you want to add a bromine, use phosphorus tribromide. It works to convert the bad leaving group into a good leaving group, where the nucleophilic substitution in a bimolecular collision will transfer the PBr2 and then the oxygen. And notice that just gets up and leaves, putting the bromine onto the chain. So this is what I would say nice to know, letting you see the mechanism. The application is what we'll be responsible for. So let's just review this one more time. If I have a tertiary alcohol and I want to convert it to a tertiary alkyl halide, so the OL converting into the halide, and we've not really moved the position of the functional group, a simple SN1 addition where I can use HBr, and through the process of protonating and deprotonating, we can eliminate the OH to add on the bromine. Tertiary alcohols into tertiary halogens. Let's go down and review SN2s. If we had a primary alcohol, same reagent, HBr, in a bimolecular collision, we could get 100% of the product inverted if it is a chiral center and form the primary alkyl halide. Very similar, just result as up above. The pathway is all that is different. Now, what if we started to use secondary alkyl halides or secondary alcohols? We have just more things to consider. We talked about zinc chloride as a catalyst for HCl, only for small molecules to deliver chlorine. If we have larger molecules to deliver chlorine, larger molecules would require a tosylate compound, or to deliver chlorine, you could use the thionyl chloride method. Either one will deliver a chlorine just fine. And if you wanted to deliver a bromine, you would use the second choice here, the phosphorus tribromide. Those are the reagents. Make sure that we have those solid on your note page to start using them as we go forward. So let's do a for example. What reagents would you use to accomplish the transformation? So again, we're changing the functional group, so I'm moving from an alcohol to an alkyl halide. So the functional group has changed. We had a secondary alcohol converting to a secondary alkyl halide. It did not move position on the carbon backbone. It's still in the same position. It's just changed its identity. So we've analyzed the substrate, primary, secondary, or tertiary. We located it and identified as a secondary alkyl halide. Does that tell you SN1 or SN2? To be an SN1 mechanism, we needed it to be a tertiary alkyl halide. The carbocation is stabilized with an SN1 mechanism. SN2 would be the preferred choice because it is a secondary alkyl halide. It also works well for primary alkyl halides. And I also notice that the wedge on the alcohol is only showing the dash on the chlorine. So we have a 100% inversion of the chiral center. Both of those reasons are telling me that SN2 is going to be my mechanism of choice because I have a secondary alcohol and I have 100% inversion. That means I need an SN2 mechanism. So now I need to identify the reagents that will achieve this step. So that's our previous slide, your set of notes. It said, if I have an SN2 mechanism, how am I going to go about, oops, I went ahead instead of back. How am I going to go ahead and get that conversion? And this is the slide I was trying to show. These are our reagents. I said we want to bring our eyes down to the SN2. An SN2 with a primary alcohol? Well, no, because it was secondary. What about going down further and finding those SN2s for a secondary alcohol delivering a chlorine? Well, this certainly looks like it would work. We could use a tosylate compound in a workup of pyridine and deliver a chloride as the substitution. There's another good choice. Keep looking down. To deliver a chlorine, we could also choose the thionyl chloride in a workup of pyridine. So again, as usual, many syntheses actually have multiple correct answers. And it's just becoming more and more familiar with your toolbox. Since this is a secondary alcohol, we know it will require an SN2 mechanism. And the stereochemistry we learned also requires an SN2 mechanism because there's 100% inversion of the chiral center. That left us with two possible synthesis pathways. The first being to tosylate the alcohol to convert it into a better leaving group, where the chloride nucleophile would then attach there and force the leaving group to leave, accomplishing an inversion of a chloride. Same mechanism really, just SOCl2 followed by a pyridine accomplishes the same thing. Now I made a note here about what would not work. We can't add HCl across the bond in a workup of zinc chloride catalyst because simply this alcohol has more than 6 carbons. That particular pathway involves solubility with water and it only works for very small alcohols. So we could not choose that third category there of zinc chloride with HCl just based on its solubility. So you've got some practices there to continue working on those reagents. I'd encourage you to look at your skill builders to bring mastery to section 9. And here's our last section, reactions of alcohols, oxidation. So remember, as we spent time learning about oxidation and reduction in terms of how to keep track of bookkeeping of electrons, this is the opposite of what we spent time with in section 4, reduction. Reducing the oxidation state on the number line is a force of reduction. The opposite is becoming more positive on the number line. for your oxidation number is known as the oxidation process. And I'd like to just share some oxidative reagents in this particular section. So oxidation and reduction are reverse of one another's. If we start with a ketone, we reduce it to produce the alcohol. If we start with the alcohol, we oxidize to produce the ketone. So they are indeed reversible reactions. The outcome of oxidation going in this direction depends upon the starting alcohol. We have to decide how many hydrogens are attached to the carbon attached to the alcohol. Is it a primary, secondary, or tertiary alcohol? So let's begin with a first example of a primary alcohol. The carbon that's attached to the hydroxyl group is attached to 2 hydrogens. Another way of saying that, the carbon that's attached to the alcohol is attached to just 1 other carbon. So I notice that we have actually 2 hydrogens, 2 sites of oxidation that are possible. For each of these hydrogens, we have a site of oxidation. A primary alcohol, when oxidized, and that will come up in a moment. This will be a reagent that we have to yet introduce. We're just getting an idea of what oxidation means. To replace one of these carbon-hydrogen bonds to a carbon-oxygen bond is oxidation. You're increasing the number of bonds from C's to O's. You produce an alcohol. The alcohol goes to the aldehyde. There's still one more hydrogen that can be oxidized, and that would lead us to a full-blown carboxylic acid, COOH. So the process of oxidizing a primary alcohol, we have the primary alcohol having a carbon attached to 2 hydrogens, primary alcohol, and it would lead to the aldehyde, the RCOH, and finally all the way to the carboxylic acid of COOH. Now with a secondary alcohol, the carbon that's attached to the hydroxyl group is attached to just 1 hydrogen. So we only have 1 site of oxidation. And so therefore, the ketone that forms is the end product. There is no next step to the carboxylic acid because there's no second hydrogen that can be oxidized. With the secondary alcohol, we have just 1 step for full oxidation. And with the tertiary alcohol, because there are no hydrogens on here at all, this reaction cannot proceed. An oxidation process changes a CH bond into a CO bond. That's the process of oxidation. And with no hydrogens available, there's no possible reaction. So just to reinforce, if I have a primary alcohol, I have an aldehyde and the carboxylic acid in a step 1, step 2, 2 conversions due to the 2 hydrogens available. In a secondary alcohol, there is just 1 hydrogen available, so a 1-step oxidative process to form the ketone. And since tertiaries have no available hydrogen, no oxidation is possible. Now, what are these oxidative reagents? What are these mystery reagents up on the arrow? Well, let's introduce some of those to you. The reagents available, we'll talk about 3 of them. The first of the 3 is called chromic acid, H2CrO4. Comes from the polyatomic ion chromate. And when you see a chromium, the chromium ion here, which is CrO4 2 negative, it's this chromium that serves in the key role of oxidizing. Some of the ways you might see chromic acid on an arrow, you might see it in its salt form, such as sodium dichromate. Sodium dichromate is a salt made up of 2 ions. Here is the acid workup in an aqueous solution to create the acid. So if I see a chromium compound, know that it's just another way of writing chromic acid. Here's another way you might see chromium sitting on the arrow. You'd have it as a compound itself. Chromium with a +3 charge here, so you have chromium oxide and a workup of an acid in a solvent of solvent of acetone. These are not numbered steps. So the solvent and the reagent are all in the same reaction vessel. So the chromium in a form of an acidic solution oxidizes. Now let's take a peek at what we see. Here is a secondary, just as an example, a secondary alcohol. So I have just one available hydrogen. The chromium, what it will do is very similar. It's going to attach onto the hydroxyl group to turn this poor leaving group, into a more stabilized compound. And so we're just adding on to create a chromate ester. That's the fast reversible reaction. In stage 2, here's the job of the solvent water. In an elimination process, is going to abstract that hydrogen. See how it's generating the acid catalyst again? Forcing this bond to collapse, and the leaving group leaves. And there's the pi bond that forms the ketone. So the first step, the chromium attaches on to the oxygen. And then in the next step, the water is going to abstract a proton, forcing the bond to collapse, and generates the ketone. Now what's interesting with a primary alcohol, because we have 2 hydrogens available, what we'll notice is that you'll have 2 sites of oxidation. The first step will be an aldehyde. The next step will go on to a carboxylic acid. So chromium, very indiscriminate, is going to oxidize all carbon to hydrogen bonds. And so this here is very difficult to stop the reaction at the aldehyde phase, and it just quickly proceeds on to the full-blown COOH. Chromium, we cannot use a chromium compound if our goal is to stop at the aldehyde. We can't stop it there. It's impossible to control that way. So what do we do if we want to isolate the aldehyde and not go all the way to the carboxylic acid? So that's why I'd like to introduce 2 more reagents that can accomplish that it can actually stop the reagent, the process here at the aldehyde. The first of that is called Pyridinium Chlorochromate. You'll see that written as PCC. Pyridinium Chlorochromate. Hear the chromium root word in there yet? It's dissolved in methylene chloride, CH2Cl. So instead of using an acidic form of chromic acid, we use a basic form. Pyridium, of course, has nitrogen base in it. And what we can see, the nitrogen down here, that we have a different mechanism that we can then control to stop at the aldehyde. So it's very selective for one oxidative step, and then it stops. So it will oxidize the alcohol and form the aldehyde, and then there is no next step. There's no next step to go to the carboxylic acid, so we just stop with the aldehyde. So this reagent is selective for oxidation of the alcohol, but will not oxidize a carbonyl functional group. If I start with a secondary alcohol, that means there is just one hydrogen available for oxidation. One hydrogen means we're going to produce a ketone regardless of using a chromium-based product or using pyridinium chlorochromate. But there is a key difference. If I started with a primary alcohol, just to remind ourselves, if this were our strategy, the primary alcohol, in the presence of your sodium chromate, in a workup of an acid in water, and we're going to come down and compare it here, this will form the aldehyde because it's primary, so that one of these hydrogens still remains, and then immediately goes on to form a second product of the COOH, that we have both steps in oxidation, 2 hydrogens, 2 oxidative steps in a chromium acid. But remember, if I had PCC in the dichloromethane, CH2Cl2, we stop at the aldehyde. There is no second step, and that's the end of that particular reagent. So there is an advantage. If you want to stop at the aldehyde, you can do that with a careful selection of the reagent. There's a drawback to this whole mechanism of using chromium-based oxidative reagents. Any of the previous slide contained chromium. They're environmentally hazardous and they require very special disposal. It is critically important to keep them out of the water supply. If you ever watched the movie, the lawyer Erin Brockovich. No, I'm not remembering her name, but this was a chromium-based poisoning, and that story was just trying to make the chemical company do well by them. That was about chromium, hexavalent chromium. I don't remember, but hopefully that movie rings a bell with Julia Roberts playing a lawyer. Well, not really, a lawyer's assistant. Anyway, that digress. I'm sorry. This is a chromium-based product, very environmentally hazardous, so we try to avoid using them. There are 2 alternatives, but each of these have their drawbacks. So 2 more green, making environmentally friendly alternatives. Let's present both of those. The first of those 2 is going to be a Swern oxidation. And it uses dimethyl sulfoxide, and you've seen this before, DMSO, dimethyl sulfoxide. And it also uses an oxalate chloride. So here's your DMSO, oxalate chloride. And then in a second step, you see this compound, just to kind of give it a visual for you, triethyl nitride. So as step 1, using DMSO in a workup of oxalate chloride, followed by ET3N. What happens in a Swern oxidation, very similar to the PCC of the last slide, a secondary alcohol undergoes oxidation once and goes to the ketone. A primary alcohol, even though there are 2 available hydrogens, only oxidizes once and stops at the aldehyde. So we have the same exact outcome as we did for PCC, same exact outcome where we had 1 oxidative step and stopped. So why aren't we using this all the time? Well, the drawback for it is that it's pretty inefficient. It doesn't yield to the same quantity of product as a chromium-based reagent would. Plus, it's a very foul odor in the lab when you're using that particular compound, a sulfur-based compound. It just stinks. And so advantages, yes, it's a little greener, but disadvantages as well because your yield is not as high and it's a very stinky reagent to work with, you know. And if that were your full-time job, it might matter. So a second oxidative reagent is known as the Des-Martin periodinane. Now hear this root word, iodine, iodide. It's an iodine-based compound, not chromium at all, but iodine. Des-Martin periodinane is the name of that compound. And you'll just see it as DMP on the arrow. Des-Martin periodinane. Same outcome. Here we have a primary alcohol converting to an aldehyde. DMP is sitting on the arrow in a methylene chloride solution, CH2Cl2, alcohol into aldehyde. In a secondary alcohol, even though we have 1 hydrogen available, a secondary alcohol has 1 hydrogen available, you produce the ketone. Primary has 2 hydrogens available, but you still stop at the aldehyde. So it will oxidize the alcohol bond, but cannot oxidize a carbonyl bond. And that's true for the last 3 sets of reagents. Now, what's the drawback? It's very shock sensitive. Any type of friction, very much like TNT, is shock sensitive. It can explode if not properly handled. Alternatives are more green to the chromium, which is environmentally unfriendly. And these are some alternatives, and we should be familiar with them as well. So lots to choose from oxidative reagents. And really the story comes down to predicting the major product from an oxidative reagent. And just knowing the product is just as simple as looking at the reagent put on the arrow. A chromium-based product is not selective at all. It's going to oxidize any available hydrogen. So here is a secondary alcohol. There are 2 hydrogens on that alcohol. I'm sorry, I called that secondary, but it is indeed a primary alcohol. That's why it has position for 2 H's. Its carbon is attached to just one other carbon, so it's a primary alcohol. That means for every available hydrogen, we'll have an oxidation occur. In your first step, the oxidative process here converts the OH into the aldehyde. But in a very next step and very quickly, we convert that second, oh Linda, that's just an O, that's the carbonyl carbon, and this then forms the carboxylic acid, COOH. So we go on to form carboxylic acid. 2 steps of oxidation. So step 1 of oxidation goes to the aldehyde. Step 2 of the oxidation forms the carboxylic acid, COOH. Selection of the reagent determines how many oxidative steps you will form. So a chromium-based reagent oxidizes all hydrogens at that alpha carbon. So the final product is COOH, the carboxylic acid. I cannot isolate the aldehyde. You have some to try. This is your last homework question in there. It's the skill builders from this section. What would the compounds make? And all I'm asking you to do is to remember chromium will oxidize all available hydrogens. Every other reagent that we looked at is selective to just the alcohol oxidation and not a carbonyl carbon. So for example, here's my cyclopentane with the alcohol coming off at carbon 1, cyclopentane-ol, and the reagent involves chromic acid. So with this particular reagent, here's a carbon. It's attached to 2 other carbons, giving it a position for just 1 more hydrogen. With that second structure there, the secondary alcohol, there is only 1 available hydrogen, and therefore the final product is going to oxidize just that hydrogen, turning the secondary alcohol into a ketone. Same idea here. This is the carbon that's attached to the hydroxyl group, and this carbon is a primary carbon. And so there are 2 available hydrogens there. However, the selection of the reagent, DMSO, will only oxidize a carbon hydrogen, but it cannot oxidize a carbonyl. So this is only 1 step. So even though I have 2 available hydrogens, the selection of my reagent says this carbon will turn into an aldehyde and stop. Here we have a secondary carbon, the carbon that's attached to 2 other carbons, making it a secondary alcohol. There is just 1 hydrogen available, so it will also turn into the ketone. The carbon then is a pi bond out to the oxygen. And you have some more to try there. I won't do them all. Notice that this DMP does not touch the carbonyl. This is a no oxidation state, but it will be able to oxidize this carbon that's attached to the hydroxyl group. And it will do so by converting it into an aldehyde. And that's it, my friends. You've got now the material to complete your Chapter 12 work. I enjoyed working with you. Good luck on your homework.